professor of electrical engineering at MIT. He is very well known for his textbook, which he co-authored, called The Structure and Interpretation of Computer Programs, (SICP), which was used for several decades at MIT and has been translated into many languages. As it turns out, he had a student that some of you will recognize the name Guy Steele, and together with his student, they invented this really awesome language called Steam, which some of you may have heard of. So without further ado, can we please have a very warm welcome for Gerald J. Sussman.
Thank you. Well, this sounds like fun. One thing that's interesting is I've been programming computers for a ridiculously long time. I've been programming computers since, I suppose, 1962, when the then undergraduate, eventually my provost, Joel Moses, was an undergraduate at Columbia, and he taught a class in computer programming for high school students. I don't know, that mic is not necessary. If you can't hear me, that's a problem. Okay?
Your ears.
Okay. Fine. Okay, because no, this mic is to make the videographer happy, not for. I do not like to get amplified. Okay, in a room. So anyway, Joel Moses taught this class, and I learned how to program on a 650 data processing system, IBM 650, which had 2,000 decimal words of, I suppose, 10 decimal digits represented in biquinary on a drum, on a 2,000 word drum, and the drum took 12.5 milliseconds to turn around. Okay, and that was the so there was an assembly language which involved two addresses, one of which was the next instruction location, so you could optimize your program so the next instruction would be just after you've done this one. Okay, so that was my original experience with programming. But I've programmed almost everything since then, and as a consequence, I've learned more ways to screw yourself with a computer than almost anybody I know. Okay, and that's really what I want to talk about today, because it seems to me that one of the biggest problems people have with programs is writing programs that are dead ends. A dead end, what I mean by a dead end is you've written this big complicated piece of software, okay, and then the world changes and something else is needed for it to be done, and then you have to rewrite a big chunk of it. Okay, and there's something really wrong with that. It just shouldn't be that way. I mean, by contrast, consider the human genome. Okay, here we've got a gigabyte of code, so that's not much bigger than, maybe it's about the same size as GNU Linux. Okay, so let's say you got about a gigabyte of code, and it's the instructions for building you as a very, very complex machine out of a single cell, okay, operating that machine for approximately 70 years reasonably well, fending off attackers that are trying desperately to eat you, okay, and things like that. You know, eventually it fails, that's true, but the bottom line is, and oh, better than that, it doesn't have version skew. Okay, that is, supposing I took half of Ubuntu 14.04 and the complementary half of Red Hat 23 and put them together, okay, you think it would work? That's how you make more people. Okay, okay, so there's something very wrong with the way we program, and I'm sort of worried about that a lot. Okay, that's one of the things I'm thinking about today. But the other thing is, I sort of do want to contrast this with biological systems more interestingly, but the fundamental thing I'm worried about is flexibility. Flexibility is the key thing that's very different that I want to concentrate on, that is not, I don't care about provability of correctness. It doesn't mean that that's not a good idea. If I have a garbage collector, it better be correct. No, that's right. And there are things that, you know, sure, you want red blood cells to work too. Okay, there's a few things that have to work, but on the other hand, most of the time, correctness is not the issue. Security may be somewhat of an issue, but maybe the way you do that has nothing to do with proving little theorems about cryptography. I mean, after all, any good locksmith will tell you that, you know, if your door has got a very good lock on it, the easiest way to get into your house is to break the window. Okay, so that doesn't work either. So here's what I'm really worried about. I'm worried about acceptable behavior over a much larger class of situations than was anticipated by a designer. Okay, that's really what I care about here. Okay, and so I want things that have the property that if you got something and it works, it does the job you want, and all of a sudden the problem changes, I want it be not too hard to make it work for the next thing. Okay, now consider this character. Okay, this is a relative of mine and yours. Okay, he's a vertebrate, so he's got the same body plan as we have, meaning that there's a nose and a tail, and he's got a spine going down it, and all the same organs that we have, and everything like that. We're really pretty much the same creature. It's not, in fact, it's not very much different from us. Look, even for in a simpler case, you take a human genome, change a little bit of it, and all of a sudden you got a rabbit. Okay, so it's very flexible, and this is a little bit more than the rabbit change, but not much. Okay, to make one of these. Okay, so this is pretty interesting. Here we have body plans in engineering. Here's a very famous body plan every electrical engineer knows. This was invented by Major Edwin Armstrong in 1918. It's the standard radio receiver body plan. Okay, it's used for audio receivers is the way it's written here, because that's an audio frequency amplifier you see there, and that's a loudspeaker. But that could have been a video amplifier in a display. That could have been a FM detector rather than AM detector. It could have been something that did something with digital. Okay, I'm not really worried about the details. The important thing is that there's a plan. Okay, and of course, my friend over here has the property that he has the same body plan we have in a very deep way too. He has exactly the same Hox gene sequence that we have. Does everybody know what a Hox gene sequence is? Okay, there's a sequence of genes that almost every animal past a sponge has. Okay, and they're actually in sequence on a chromosome in the same sequence as they are. They represent the regions from the nose to the tail. They divide up the creature into regions. They don't say anything about what goes on in those regions. Okay, it's just that they're the coordinate system. And this guy, of course, we'd expect the same plan we have. It's not so clear later. We have ideas about this. We do all the time. Okay, by the way, if you don't like programs appearing, you should walk out now because there's going to be a lot of code. Okay, and a lot of it's going to be about parentheses. But in any case, here's a composition operator, which you all know what a composition operator is. Okay, f of g of x is the composition of f of g applied to x. Okay, and indeed that's sort of a little piece of a body plan. You can have more complicated ones like tensors and things like that. I don't really want to go into that, but we understand a little bit as engineers what a body plan is. It means that we're specifying the outline of something without specifying the inside. Okay, and that's very important. Here's a guy who's actually a little bit more different from us, quite different actually. This is a hemichordate called an acorn worm. Well, what can I tell you about this? It turns out he has exactly the same Hox sequence we have. Okay? However, he's got his kidneys in his nose. Okay? So again, you're just trying to explain the idea there that now that means that there's a kind of thing I want to be able to talk about today which has to do with being able to diddle the underside of something that's already laid out. Okay? This is a very dangerous kind of manipulation. But it's a kind of thing that gives you a tremendous amount of flexibility. And I said I'm going to be willing to trade off almost everything for flexibility. So I want to be a really nasty programmer today. Okay, so I'm going to talk about this. Okay, this is an idea that Chris Hansen and I have been talking about for a very long time. Chris is the principal author of MIT GNU Scheme. Okay, so just for those of you who don't know. Okay, and he now works at Google, although he worked for me for 26 years. And we're writing a book together on stuff like this, on flexibility. But in any case, I want you to remember this idea. A diamond is very pretty, but it is very hard to add to a diamond. A ball of mud is not so pretty, but you can always add more mud to a ball of mud, which I learned from, in fact, Joel Moses or Paul Penfield, I don't know which, at an APL 79 conference. They said that one of them said that, and I can't remember which one. Okay? So that's what I want to talk about. Now I'm going to start with an illustration of a particular numerical process. Again, I don't know how many of you actually know a lot about numerical things, but I do a lot of that. because I like to push planets around in orbits and things, celestial mechanics. But I'm going to show you a simple one here, one that it's small enough you can fit on a slide. This is a ordinary differential equation. The second derivative of the x function applied to t is some function of time and x of t. Okay? So basically, all I need to know is time and the position at this time to give me how it's accelerating, whatever this object is. It's Newton's laws. Okay? All Newton's laws look like that, and the x can have a gazillion dimensions for all I care. Okay? It usually does, because it's 3 dimensions for every particle or whatever you like. Now, I might want to discretize this so I can integrate it numerically. Okay, and one way to do that, of course, is to make a discrete approximation to a second derivative, which is what you see there, right? That's that I can have, when h is the step size that you see, okay, then I can say take a little bit of x ahead of now, and the current one, and a little behind, make a linear combination of those, divided by h squared. That turns out to be a good approximation to a second derivative. And then I can say that's really a linear combination of various past values of the acceleration. Right? That's a particular one. Stormer's method, for example, Stormer's second two-step method, there's ones up to 20 steps. Okay? But Stormer's two-step method is a simple version of this. It's that the next position can be computed from the previous position and the current position on the previous position, but multiplying by some magic numbers and a linear combination like that. Okay? Those magic numbers are selected by numerical analysts to get the appropriate behavior of converging to the right answer, for example. Okay? That's easy to write such a thing. Okay, so you can write, this is a Stormer integrator. It takes a history of states of the system, okay, and you take 2 times the current value of the position minus 1 times the previous position, multiply h squared over 12 by the linear combination of the accelerations for the current time, the previous time, yes, and the previous minus 1 time, okay, the penultimate one there, and that's how you write such a thing. It's pretty easy and it works pretty well. Okay, in fact, now the reason I'm bringing this up is because I'm going to show you some interesting things with this. So here we go. I can make a thing that evolves this thing. If I take the integrator, okay, and I have a function that actually makes the integrator here, and I'm going to pick out that integrator, make a stepper out of it, and then I have a little loop. This is a loop in well, this is the evolver. It's going to call the evolver. Actually, the loop's down here somewhere. Okay? No, that's right. The evolver is here. So this is the evolver. It takes a history and number of steps I want to go advance it to. I say, gee, have I gotten there yet? If so, I'm done. I'll just return the current history. Otherwise, I step the history along and n minus 1 steps. Okay? And I'm returning that procedure, the procedure which is the evolver. Okay? And indeed, and again, you don't have to gobble this up completely right now, although it's easy. Okay? This is not complicated programming yet. There'll be some complicated programming shortly. Okay? And then what happens, I have a stepper here, which extends the history, given a particular history, it extends it by an appropriate step, by 1 step. Okay? And that's what's being called here. Okay? So look at that. Now here doing it, I'll take a very simple case. The simplest case here is, well, what do I have? I have here a harmonic oscillator. Right? The second derivative of x is minus x, actually. Okay? So that means the answer is sine. Sine is one possible answer. Of course, there are many possible answers, but sine of t is an answer. Okay? And so I pick one that's simple enough to understand. Okay? And define that f to be that. I'll make an initial history for myself for starting at time 0 by 0.01. I have sine of 0, sine of minus 0.01 to minus 0.02, so that's an initial history. Okay? I'm going to evolve that thing and look at the x value of it, and that gives me sine of 100, or sine of 100 times 0.01, which is 1. Okay? Sine of 1 is that's not very far apart. It's good to 10 to the minus 7th. Okay? So there's an example of a very simple process. Now, why am I showing you that? Because I'm saying, supposing you built this thing. Now, let's ignore the fact that I've given you a completely trivial thing to integrate. And it really, if I were doing something like the solar system, I might want a 12-step integrator or something like that. Okay, and I want step sizes of, like 1 day or something, and I might worry about that sort of thing. But by golly, what I'm going to show you is that it doesn't take very much to turn this into a symbolic machine. Okay, and in fact, it's trivial. Now, unfortunately, I'm running off the bottom of the slide. That's interesting, because on my display it's not doing that, and I've never used HDMI before, and I see what's happening is, does anybody know what the right thing to do here is? Maybe not, but I've got an idea. No, I've got a better idea. The better idea is to help with this thing. I am going to, yeah, that's better. That's better. Okay, it's a little smaller, but you're seeing the whole thing. Okay?
Zoom in.
Zoom in what sense? Oh.
The image. You're not filling up your whole screen.
I don't care. The problem I was worried about is I was worried about is because these are big enough. Okay, I believe these are big enough. Everybody see this?
Yes.
Good. Okay, fine. Okay, so here, what I'm really going to say is the following. Assume for the moment that I've arranged my system. I've arranged my system so that all the numerical operations in my numerical library are in a package. Okay? Where a package is nothing more than a mapping of names to the procedural values of them. Okay? It's some kind of mapping that tells me what each name means. So plus means the thing that adds. Okay? But that's up to me to decide. Okay? Now, if that's the case, supposing what I can do, for example, is I can make another arithmetic package, okay, which happens to be a symbolic package. Just give it a name, symbolic. That's all it says there. It's being built on top of numerical arithmetic, okay, whatever that means. We'll talk about that in a second. Such that for every procedure in the numeric package, okay, it has a name. I'm not even going to worry about the fact it's a numeric package right now for this case. Okay, the thing for that name will be a new procedure of any number of arguments, which constants the name onto the arguments. Okay, isn't that obvious what that does, right? It's basically building the parse tree of some algebraic expression. Okay, so now if I've done that, now here's something nasty. Okay, a lot of people are going to get mad at me because I'm going to modify all of the bindings in one shot. Bang! All my numerical procedures are now symbolic ones. Okay, that's dangerous. Okay, you have to understand. I understand this is dangerous. Okay, and we can worry about that in a minute. I assure you that I believe that sometimes the danger is worth it. Okay, because we do this all the time anyway. We have generic operations in most of our languages where we have mixed, floating, and integer arithmetic, fixed point, perhaps. Okay? That's terrible. By golly, if I can have a thing that works just great for the integer arithmetic, and if I try to use floating point, it's going to do the wrong thing sometimes. Okay? We know that. How many of you know that the average of two numbers in floating point may not be necessarily between them? Does anybody know that? Okay, for those of you who know, here's a good thing. 996 times 10 to the 0, imagine 3-digit precision, plus 998 times 10 to the 0 is 1994 times 10 to the 0. Correctly rounded, that's 194 times 10 to the 1. Divided by 2, that's 995 times 10 to the 0. Okay? Now, I just want you to understand that, okay, so the only reason, watch out. People, I wouldn't get into an airplane unless it was a test pilot and you tried it out. Okay, floating point doesn't impress me. But in any case, so we do this all the time, but we don't realize that we're being dangerous. And of course, if I write a numerical process that depends upon the commutation of multiplication, then of course if I put in matrices, it may not work. In fact, won't work. So I got to be careful when I do these things. Sometimes we have to live dangerously. Okay, but in any case, I'm installing that, and now I say, oh yes, what is x0 of the result of evolving the Stormer thing one step from an initial history which is entirely symbolic? Bing, I get a symbolic result. Okay? Now, it's not simplified. I could run it through a simplifier. That's a different problem. But I've got something, oh yeah, negate just happens to be the minus 0. It's a unary minus. Okay, but that's that's a separate thing. The fact is that this is a very simple process. Of course, I've given something up. We'll fix that in a second. Okay? In particular, the symbolic operators can't do numbers. Right? But I'm going to start elaborating this process for you. Okay? So what do we have here? We have numerical arithmetic, appropriate, and symbolic arithmetic when appropriate. So what we really want to do is attach to every operation an applicability predicate that says whether or not it does the job. And I can make sticky notes pretty easily. You know, what most people think that the right thing to do is make careful record structures that have all the right slots in them and things like that. You know, that's nice when you know what you're doing. 99% of the time you don't know what you're doing. So the right thing, my view of the world, again, I'm being very extreme today. What I do to make sure that everything is really flexible is I do this with property lists. That is, I have some hash table, okay, and I'm making a double entry hash table, and so I'm attaching to every object the thing that's EQ, okay, with a property, and by golly, now I've made a sticky note that I stick on the thing. Okay, so I can find out what things are and what things are not, and whether or not they have this particular applicability property, and so on. Okay, so I'm going to make such a thing like that, and now I'm going to make up a new kind of arithmetic maker that actually has an in-domain predicate I'm going to pass in. Okay, so for example, I'm making numerical arithmetic. I obviously want to say test for a number. Okay, if it's symbolic arithmetic, well, that's not the same thing. I'll test for being symbolic. Okay, whatever that may mean, and we'll worry about that in a second. Okay, so I would have those things in there, and then I can write down my numerical arithmetic. Here's my numerical arithmetic package. It's an arithmetic starting with the name numeric. That's just a debugging name, so when I'm chasing around inside the machine, I can find out what it is, what I've got. Okay, but I built out of the raw schema arithmetic structure. It has the applicability predicate number, and now it's replacing every operation. Okay, with every operation of name with the thing that has the appropriate base operation for that name. Okay, because I'm not saying how I'm going to build this. It might be I'm building numerical arithmetic over something else. Who knows? Okay, but in any case, okay, I'll pick out that base operation, and I'm going to return the new object, which is an annotated version of the procedure that applies the base operation to the arguments with an applicability that says every one of the arguments for this base operation, whatever its arity is, how many arguments it takes, is going to be one of the things that's in the domain, according to the in-domain predicate. Now I'm leaving a lot of space for lots of things I'm going to add. Okay, so you don't worry about this yet. And of course, so then it looks like, you know, why did I have to do that? Well, we'll see. You'll see later. Okay, so then symbolic arithmetic, I can make parametric over the base arithmetic, like this. Okay, and what you see here is that the symbolic arithmetic, well, I'm making a thing called symbolic over the base arithmetic, which right now in my head is numeric arithmetic, but it might be something else. It might be matrix arithmetic for all I know, right? But then it tests for the word symbolic, and it's going to say, well, over that, they take over for every name in there, pick out the base operation, annotate const name argument, that procedure, which is the one that makes up my symbolic representation, with an applicability that says any one of the arguments, if any one of the arguments is symbolic and all the others are base. Okay? Okay. By the way, if anybody wants to ask questions at any point, I'm perfectly happy to try to answer anything you ask. Huh?
Turn up the microphone.
Why, you can't hear me?
Hardly.
Really? That's amazing.
You want to shout?
Yes, I'd much rather shout than have a microphone. I'm surprised. I talk in rooms with much bigger than this all the time. Okay, maybe this room has bad acoustics.
Look up, you can see why.
I don't know. That doesn't say much.
It disappears into all that crap.
Oh well. Okay, I will talk louder. So anyway, I can also now I make some combinators. Like we had combinators like compose originally. Compose was a very simple one, but here's a nice one that adds two arithmetics together. I started with two arithmetics, A1 and A2. The name of the result here is add. It's got two previous arithmetics, a list of those. And the new in-domain predicate is the disjoin, that is the new predicate whose value is the OR of the values of the two given predicates I gave it on the argument. Okay? And this builds this new thing which says pick up a base operation, each of those, and I'm going to dispatch on the types of these somehow, okay, by their applicabilities actually. And then the operation dispatch is going to be something that's very simple. Okay? It's going to say, it's going to do, unfortunately it's going to have an order. That's bad. I apologize. Okay? It does cause trouble. Okay? So there is some ordering I'm putting in here. But it says basically if one operation is applicable, use it. If the two operation is applicable, use that. Otherwise, I've got a bug. Okay? So this is just so far I'm building up structure here, and now I can add a little bit more setup. I can extend arithmetic, which basically I'm extending a base by an extension, where an extension is a procedure that takes a base and produces a new arithmetic. For example, symbolic is such an extension. Okay? And now, so I can start with something like numeric, extend it by symbolic, okay, and that adds those together, and I can to combine those, I do that. Okay, I make a new combined arithmetic, and I'm going to install that one. Now you see what really is going to happen. Okay? Now this is, by the way, something I teach classes in. Every spring term, I teach a class on things, but games like this. And the reason I do that is because I'm in opposition to the standard belief structure of computer scientists, okay, who think you shouldn't do things like this, okay? And the reason why I worry about that is because I think they're worrying about the wrong things most of the time, okay? What I want to make sure is that it isn't the case that I'm going to spend the rest of my life, and everybody who's a programmer spends most of his life fixing code that he's already built, or that somebody else has built. Okay? Which is, in fact, it shouldn't be a problem. It should be easy to do that. The hard part should be coming up with ideas and organizations that don't have this problem. And the inspiration, by the way, is Emacs. Emacs is a gorgeous program explicitly because of the fact that 10,000 people have written parts of it at this point. And guess what? It still works and is reliable. Yes. Yes.
This sounds marvelous.
I'm not done. It'll get more marvelous.
In situations where, for instance, you're going to write a big flight control system. Anybody could write a big avionics package.
Let's get avionics. That's better because that's got less safety critical.
Yeah.
That's even more interesting.
Right. Or okay. Some medical software. You're going to write, defib software.
Well, that was less interesting, but the avionics one's more interesting. Okay.
So, in the real world, the Raytheons and the Lockheeds and the Martin Mariettas will sort of look at you and go, "There's no freaking way I'm going to put list my
aircraft." That's exactly right.
But they will inherit methodologies that give them ability and robustness, but field programmers are going to stick to their C and their assembly,
of course,
or whatever, and they're going to take their sort of decades-old methodology to develop these things and dispatch them because, well, we really don't want to kill all those people on the plane.
Yeah, I agree, and I want to point out something very different, though. I think that the people who think that the avionics software, for example, the autopilot, should be perfect, are wrong. Okay, and I'll explain what I mean by that. Okay, now it doesn't mean I can convince them. That's a different thing, because remember they also have liability problems. Okay, a lot of what goes on in the world is determined by lawyers. Right. Okay, and that's a real problem. And as Shakespeare had an idea about that, right? It was Henry IV, Part 2, right? Act. I don't remember. It says first we killed the lawyers. Okay, but the problem is that in avionics software, so let's consider an autopilot, for example. Okay, it's designed to work perfectly when everything is going well. Okay, now recently, meaning a few years ago, an Air France plane had a pitot tube die, so it got inconsistent information about the airspeed. This caused an autopilot to basically turn itself off. Okay, because the autopilot said, "Gee, I don't know what's going on here." Now, of course, there's plenty of information. and plenty of information from lots of things that it could have known what was going on. But its job was to not do it, was to do nothing unless it knew exactly what to do. Unfortunately, the pilots did not understand what happened, and they crashed the plane in the middle of the Atlantic Ocean. That's what happened. Okay? The right answer, as far as I'm concerned, is that the autopilot should not have turned itself off. It should have done something reasonable. Okay? It should have tried to fly the plane at constant altitude, okay, and heading, which it was perfectly capable of doing because it had enough information to do that, and informed the pilot that something was wrong, that was getting inconsistent data. Okay? That seems to me to be the right thing. And the fact that it should try rather than erroring out and crashing is actually, it seems to me, the wrong response. And a lot of the stuff we build is built basically to turn itself off, so it is not responsible for causing the problem. So that somebody's lawyer doesn't get to sue that guy.
Let me ask you a question. This methodology, for example, have you contrasted it with things like developing shuttle flight control software? They're famous for methodology in FCS.
Gee, I haven't looked at that, but I'll tell you, I've recently been looking at stuff having to do with automobiles. I'm not going to tell you the details. I tell you the insides of automobile software is disastrous. Okay. Anyway, but that's a separate issue. But I think that a lot of the problems in the world are due to the way the legal system is structured. You have this idea of you have to blame someone. Okay? And in fact, engineers would do far more reasonable things if they weren't under those constraints. Okay? But that's a flame from a different order. Anyway, yes, because I tell you, I'm deliberately taking risks here, extreme ones. In other words, the code I'm writing here is terribly risky, on purpose, because I'm showing you the extreme end of it. Okay? Of course, I would want to put in lots of tests and checks and things that things are sensible. That's a different problem. Okay? So, anyway, I want to show you what I can do so far. This is only the beginning, of course. Gee, I'm only about halfway through. Okay, so I've got a lot to talk about here. So now, of course, I can still do what I did before. This is the original numerical history that I started with. That was the first few values of sine. And I get the same values I got before. It also still works symbolically, but it also works in combination. Okay? Meaning I could have part of the thing being numerical and part being symbolic, and I can get the result with the symbolic part being left unevaluated. Okay? So everything seems to be in a nicer state. Okay? I like this. And this is in many ways, this is the way I like to build software myself. I like to build it so I can layer it on like this, and if I got a new problem, I'm just going to add more stuff. I want it to be additive. I don't want it to be screwing around with what I already got. Indeed, in the case of this numerical stuff, which is pretty easy with algebraic or numerical stuff, it is true that this is very structured, and that makes it a lot easier than doing something more complicated. And I want to, of course, agree with that. And be careful to make sure you're all right. You understand that I understand that that's true. This is a very simplified situation. Hardly anything is as well understood as algebra. Okay, but now look. Mathematicians like to invent funny notations. So f plus g of x is f of x plus g of x. Okay, that just happens to be a convention. We get into all sorts of trouble with mathematical notation, of course. You know that cosine square x is cosine x times cosine x, but cosine of the minus 1x is not 1 over cosine x. Okay, so these people are not even consistent, but that's okay. Okay, we have to put up with the fact that traditional mathematics is a natural language, and so that's okay. But in any case, supposing I want to put in functions. Okay, well that's easy enough. I make a function arithmetic here over some arbitrary range arithmetic because I'm dealing with the values of the functions are going to be added together or multiplied or whatever. Okay, and I build for another over that whatever that range arithmetic is. I have a in-domain predicate which is function test. Function can be whatever I want it to be. I suppose I'm personally writing it as procedures, but that's my option. And the description. The description for each of these named procedures is pick out the range operation, and I say, well, if it's for a bunch of functions, if they're all the operands of functions, then for a bunch of functions, I'm applying the range operation, the result of applying the functions to the arguments. Okay? That's all that is. And once I do that, as an extension over the combined arithmetic, I can now write things like the sum of the product of b and the cosine and sine applied to 3a is, the appropriate algebraic expression. Okay, so that works too. Okay, it's just things get additive in this way. Okay, I might even want, here's the thing that mathematicians do. They have coercions. Okay, in this context, 1 is interpreted as a constant function which always produces 1 no matter what its arguments are. Okay, well, I can do that pretty easily by changing my function arithmetic slightly. What I have to do here is change any of the arguments as functions, and then have a little test inside here that walks down the various things that came in, finding out which ones are functions and which ones are not. Okay, and then doing the right thing. Okay, just giving you examples of the sort of thing you can play. And once you do that, of course, if I install that arithmetic, then I can say things like b times 4 plus cosine plus sine times applied to 3a, where a is a symbolic value. Okay, and what do I get? I get the right thing. Okay, so and this is, I have a very large system built on this stuff that I use for teaching advanced classical mechanics in the fall terms of my every year. I teach with my friend Jack Wisdom. We teach stuff starting with Lagrange's equations that goes through canonical perturbation theory and even things like differential geometry, and it's all built on this kind of stuff. So it's very simple, and students get to use it. Now you can see that I can sometimes want something like a literal function. What if I wanted something which is, so I want to interpret that c as a function? Well, I can't, because it's, I can't distinguish it from a number. Okay, well, that's a problem, and we'll worry about that later. But of course, what I could really do is make up a thing that says if any literal function is really just a thing which puts its name on something. Okay, that works. It's not very safe to do it that way. I have to do better work, and if I want to be able to take derivatives of things like that, I better know what I'm doing, and so on. But I'm not talking about that today. Okay. However, at least I've got this thing working pretty well now. Okay. So I can say I can add a number, a symbolic number or a symbolic function, okay, to cosine and sine, okay, and I can get the appropriate algebraic expression. Okay. And so here's really, I can if I have an algebraic simplifier, which is itself a complicated problem, probably far more complicated than almost anything else I'm not going to tell you how to write one of those, because sometimes an algebraic simplifier is a complicator. And it's exactly what you mean by simple depends upon what you're going to use the result for. So there's a lot of difficulty there. But imagine I had something called the simplifier, which I do, okay, then which tries to do something reasonable. Then if I take 2 steps of the evolution of a completely symbolic system with, in fact, a literal acceleration function, then I get this fairly horrible object. Okay. But if I were debugging a numerical program, it's very important for me to do this, to be able to symbolically evaluate it and examine it. And indeed, a lot of good compiler technology is in fact the same thing as simplifying a symbolic evaluation of a program. Okay? And so, I think that we should really not consider a compiler to be anything other than a fairly complicated simplifier of such a thing, with maybe a translation phase to some other language, and maybe a simplification of that language too. Okay. Okay. So now I'm going to get back to this biological metaphor, because I'm going to see what I've shown you so far looks pretty daring, but it isn't. It was very simple, and it was simple in a way that was constraining me a lot. I had to know what all the algebraic operators are going to be ahead of time. I had to have I had to have that library packaged into a package. Now that's already too much from my point of view. I want to loosen this up. Okay, and I'm inspired by this character. This is a particular frog, quite different from the one you saw before, but it looks the same, right? Frogs all look the same. This guy is Gastrothica rheabombe. He's been known since about 1913 or something, like a bird. There's a big yolk, and then there's a little flat disc that turns into the frog. Now that by itself is not a big deal. The big deal is that different embryonic tissues combine to make the organs in this frog than in the standard frog. So there's more than one way to make a frog. That's the yes, sir.
It's an argument for intelligent design. It's undergone a refactoring.
I can get to it. I'd fight with you over that one, but I think it's
points about that frog is better than any other frog.
right. I think it's what it is. It's a well. I think it is that there's the ability to tweak things under the table, right? That evolution has had has the nice feature that makes it really more powerful than what we do is you don't have to figure it out ahead of time. Okay, you build this thing called a frog, and then you can tweak it by changing the order in which things happen in the development, for example. Okay, that's pretty wild. So you make a completely different kind of frog. Okay, well you make the same frog but a different way. Okay, now, so I want to be more like that. I want to have that kind of freedom. Okay, and I want to show you some of that. So I'm going to show you this is what I'd like things. Again, this is back to my mantra for today. Okay, I want you to. Here's my ball of mud. Okay, first of all, let's say why I'm worried about this. Not everything is arithmetic. Arithmetic is very, very simple. Okay, but I can start dealing with things like sequences, which is much more complicated because I can infinite sequences. I see some closure over there. Okay, and infinite sequences are a strong component of the closure world. Okay, and they should be. They should be the same as lists. Okay, really, that's a mistake I made long ago in the scheme before I understood that. Okay, that they weren't the same. Okay, that the streams in the list should be the same. And they should have the same operators that apply to them. Okay, I have vectors, and they have different kinds of properties. Of course, vectors are order one axis. Okay, there are character strings. There are other things like that. There are various procedures appropriate for those. Okay, and the diversity there is much more complicated than what you find in algebra. Okay, but it's worse than that. Okay, you have things like sets. Okay, and that can drive you nuts too. You have things as distinct as linear lists and hash tables. Okay, that have to be sort of merged together to make one idea of how to deal with sets, where you have unions, intersections, and everything else like that. Okay. So when you start dealing with really complicated systems, more like we deal with in computation, you don't really want to be constrained by the feeling that you know all of the operators you're going to deal with ahead of time. There isn't a package. The package I'm interested in is the package of everything. Okay, I want everything to be generic and modifiable. Okay, so as a consequence, here's my ball of mud. You see, I want to be able to say things like this. I'm going to make a generic operation. I'm going to give it a name for purposes of debugging called foo. Okay, I happen to also name it foo for my access here. Okay, and I'm going to say I'll add to it. Well, if all the arguments, it's a generic operation of arity 2, and if all two arguments are numbers, then I'm going to add them. Okay, I could have written if I were being more obscure, I would have just written a plus here because in Scheme I can do that. Okay. I wouldn't have to write lambda AB plus AB because there's nothing special about plus. Okay, and then if I want it to be, if any of them is symbolic and the others are numbers, I want to be able to consign the plus onto the arguments. Okay, just like I did before, and so I get this sort of behavior. Okay, so that's a much more flexible way because I'm not assuming I know ahead of time what all the parts are. Okay. Now, so I'll have to tell you how I make this. I'm going to have the operation be a thing which Doug calls the generic dispatch, based on some metadata that's going to be stored somewhere, and on the operation. This is going to be that's a put. Okay, it says I'm attaching it by hash table or something like that. Okay, the metadata, and then When I add to a generic operation, I'm just adding stuff to the metadata, a rule, an applicability rule, coupled with a way to apply, a handler. Okay? And generic dispatch is going to go chasing down in the metadata looking for an applicable rule, and if I find such a rule, apply it, otherwise I have an error. Okay? So that's sort of, now of course there's some details to make this actually efficient. It has to be reasonably efficient, okay, and that takes clever Chris Hansen type work. Okay, basically, how do you make the compiler turn this into 10 instructions? Okay, but that's a separate issue. Okay, now I go back to arithmetic. I'm going to make new packages again. But I'm going to make packages, but now I'm going to be much more flexible. I'm going to make a package called the generic package. Okay, and it's going to be a thing called generic over the base arithmetic. Any object will be its input possible, and what it does, it pulls out the generic operation. Okay, it makes a generic operation appropriate for it. Okay, and to add to a generic operation, arithmetic, all I'm going to do is add an arithmetic to it like this. Okay, for every name in there that's in the arithmetic operators of the extra arithmetic I've got, which might be a package of things. I'm going to then go walking through this and pull out the generic operation, the other operation, and crunch them together. Okay. So it's sort of this is very flexible, and yet there are still lots of constraints here. This is not a completely unconstrained system. So I'll give you some examples of what I might do. Okay. Yes, is there somebody there? Did you want to come in? Well, come in. Here. Oh, I see. Yes. Okay. Yes, I see somebody lurking. Well, you've missed almost all of it, but that's beside the point. Okay. Okay. So, for example, here's how I might make myself a package like this. I might start with make a generic arithmetic out of a numeric arithmetic package. So I'm pulling up a bunch of operations this time. Okay. But now I'm going to add numeric arithmetic to it. That is not the same thing as I'm just picking out. Here I'm just picking out the operation names. Here I'm saying for every operation name, I'm going to add the numerical stuff. Here I'm going to add the function arithmetic over the numerical stuff. Here I'm going to add the symbolic arithmetic over the numerical stuff, and I'm going to install that, and now I get lots of things, except one bug. We'll worry about that in a second. Okay? You see, turns out I've done something nasty. What I've done nasty is I've introduced some order dependencies that are worse than the ones I had before. It depends on the order in which I build things. Okay? Oh, okay, yeah, but that's true. I have to worry about that, and that's a cost of being flexible in this way. Okay? Now, an alternate way to think, which I did not implement, and which would be fun to do, and I probably will next time I think of it. Next time I have an all-nighter to pull off, okay, which I love to spend all night reprogramming. But next time what I'm going to do is I'm going to make it so that I'll have the machine try all possible orders, okay, and see if there's any that converge. And that's the right one. Unless there's two of them that converge, then they better be equal. Okay, but because that's the way the real things ought to work. It's the same way biological systems work, sort of. Okay, if there's degeneracy in biological systems. Degeneracy meaning, like in physics, we talk about degenerate eigenvalues. In quantum mechanics, it means that there are many ways to get the eigenvalue because there's multiple eigenvectors. So, degeneracy. What I mean here is that, well, as from a biological point of view, if I failed to be able to eat sugar anymore for some reason, I lost the ability to process glucose. Okay, I can still get energy by eating proteins. Okay? Eating proteins. Yeah, it turns out that there are different pathways, and that for the most part you may not be able to survive very long that way, but certainly there are many things like that. Certainly, if I hurt my right arm, I can do a lot of things with my left arm, including write badly. Okay, so the degeneracy means there's many ways to do it. It's not the same as redundancy. Redundancy is a kidney is redundant. It's got a gazillion copies of the same machine. But if you have many different machines, each of which does approximately the same thing, that's called degeneracy. Okay, and that's a very powerful thing to build into programs. We don't do that very often.
In a sense, graceful degradation?
Yes, but graceful degradation by having more than one way to solve the same problem, such that if any of the ways fails, there may be other ways to do it. Okay? Yes, sir?
Could you repeat? I couldn't hear what the strategy was. If you're trying all the possibilities.
I was saying yes. I can imagine that writing a little sort of operating system basically that pulls out the various applicable operations for an operator, and then it turns out in any particular way I did it, some order, one way it doesn't work, I might try the other orders until I find one that does, and if I find all of them that could work, they better have the same answer. Otherwise, that really is an error. Okay? That may be something that has to be tracked down by something else. Okay? But that's another way to get around that. And but right now I'm putting up with the fact that I have an order dependency problem. Okay? Because I'm showing you the sort of real guts of this thing. You're seeing real order dependencies. Okay? So for example, I could change closure. This is a different closure. This is if I change the order, for example, I could do it this way. I could make everything generic. I can always add to the generic arithmetic and make everything built over the generic arithmetic, and that works very well. See, what I did before here was I built everything over numeric arithmetic and just added it to the generic arithmetic. But I can in fact use the generic arithmetic as my base arithmetic and then build things over that. Okay, and that gives me a considerably better organization such that all these things work. In fact, I can even do things like this. Okay. So all of a sudden things start working that you wouldn't expect. Okay? And that's the best situation. Best situation is when things that work that you didn't expect them to. Okay? Okay, but we still have an order dependency, which I have to solve. Okay, a little bit more. So I can do that with by making unambiguous rules, it turns out, by in fact changing it slightly so that the symbolic arithmetic is over the numeric arithmetic by itself. I don't want to go into the details of why this is true, but now I have something that really works for every case that I've shown you before, and it's much cleaner and easier to work with, okay? Because I can actually add to things without having known about them ahead of time. Okay, so now going back to where we started, okay? I'm going to look at the literal force law here, f, some literal function f, okay? I'm going to start with a symbolic initial history. I'm going to look at one step of the evolution. Okay. What happens? Well, if I look at 2 steps, it's getting pretty bad, but I'm already beginning to see things that I wanted to fix. As a good programmer, I don't like this because I'm evaluating this guy several times. Right? And that's the most expensive process in doing an integration. So of course what I want to do here is common subexpression elimination. Bam. Now I've got that. Okay? That looks pretty good. Okay? And by golly, yes. So I'm sort of about to converge and summarize. Okay? What I've been showing you is some very dangerous games I play. Okay? I promise. I believe that take careful but dangerous programming is actually a very good strategy, and the reason why it's good is because it allows you to try things very fast and get them to work. Okay? It is the case that there are many things that you do. Look, many of the mutations in biological systems are fatal. We know that. But basically what you end up with is a very robust mechanism when it works. There are lots of cases where this could be improved. And I'm not trying to say this is the right way to do everything. As I said before at the very beginning, if I have a garbage collector, yes, that's the case where I'm going to prove it's correct. I have to put in the effort to make sure that the garbage collector is not going to screw things up because that's very hard to debug. Okay? That's the reason. It's not because I care that it's right. I care that it's very hard to debug. Okay? It's hard to debug a program if the garbage collector fails. Okay? That's not the same. And what I want to make sure is things be debuggable, easily modifiable and debuggable very fast, with very little effort. Okay? So I'm going to talk a little about, first of all, philosophy again. Okay? There are all these things people think of as being the right way to do things. Okay? I have lots of friends who will tell me that the right thing to do is you whip the programmer until he does it right. This is the Dijkstra theory, right? Okay. Then there's people who say, well, object-oriented programming clearly is the right way to do everything, or functional programming is purely the right way to do everything. Maybe. I like it. I enjoy programming that way. Okay? But that's the thing. There's rule-based systems, there's logic-based programming, there's constraint-based programming, there are neural networks, genetic programs, Bayesian networks, I've tried all of these things. Okay? They're all good. They're good for something. Each one's good for the kinds of things it's good for. Okay? And in fact, the most important thing is a really good engineer has a pretty big toolkit. And what really matters is to use the right tool at the right time for the right purpose. Okay? And these tools have to better be able to work together. Go to a machine shop, which I do a lot. I like the machining stuff. Okay? It better be the case that the collet that goes in, that I pull off the shelf, better go into the mill in the right place and fit the appropriate taper. Okay? And if it doesn't, they've got the wrong machine shop. Somebody's done something wrong. Okay? Well, the problem we have in most programming is you try to do something in language X that is object-oriented language, but all of a sudden you need something that really is functional. It's not going to come out nice. Okay? You want something. You've got something you're going to write that's obviously should be logic programming, basically backtracking of things, and a tree search of some sort. And you've got to write it with an object-oriented thing. Ugh, it's going to look awful, and it's going to be hard to understand. Okay, and yet if I'm going to make a device driver, I don't want to write it in functional style. That's terrible. Also, it's not going to work. I don't care what there are Haskell people here who might think I'm wrong. But I will charge them with the problem of controlling a telescope, mirror support system sometime. Okay, you have to actually worry about the timing of little things that are moving around, and they better move around in such a way as not to break a $500 million mirror. Okay, I've done that sort of stuff. Okay, so there are all these magic bullets. Okay, and I'm worried about that. And the most important, here's my real suggestion for everyone. Don't shoot yourself in the foot with any magic bullet. Okay? Because nothing is the right none of these things are right for everything. Okay? What you really want is to have all of them and every other one that I haven't thought of yet. Okay? But what you care about is this. That the stuff you build is additive, and that's what I spent a lot of time on today. Late binding means I don't make a decision until I have to. Okay? The parts are interchangeable, and they easily operate with each other. That's what really matters. Okay? And all these other things are just particular theories of how to do that, which work sometimes. Okay? So I've got lots of ideas about this. As I teach a class about this, of which you've just heard maybe about a week of that class. It's a 13-week class. Okay? But I teach a class about this where I worry about robustness. And the ideas come from biology, from math, from engineering. Degeneracy is a case that I worry about. Okay? And there's exploratory behavior, which has to do with backtracking and tree search and various things like that, using combinators. And then this other thing, which I think is very important, which is to not worry so much about proofs. Okay? You have to use proofs sometimes, but don't think that's going to solve the problem of making your programs really good. Okay? What it's going to do is, in fact, it's got a bad feature. Supposing you were, again, the Mr. Dijkstra type person who says you have to prove the program before you even type it in. Okay? Okay. So what that means is that, well, in order to do that, I have to work really, really hard to make each part very perfect. But it's very hard to prove general theorems, so I make each part as specific as possible. Its inputs are very limited to exactly what they're going to be. Okay? Under those circumstances, I made a very brittle structure. I push on it and it falls over. Okay? It works just great for the problems it was designed to work for. I care about making things that work for the problems they're not designed to work for. Okay? That's the difference. And I suppose that's pretty much it for me, and that's what I want to talk about today. And I'm happy to pick arguments with anybody. And I learned something, because one of the greatest things I ever found is that my students teach me more than I know. Okay? So. Yes, sir.
Why did MIT switch from C to Python?
Oh, well, first of all, it's a much more complicated story than that. We had a curriculum that was started around 1980, which I was one of the authors of. The curriculum was a four class, 15 hours per class, hours per week, okay, class. Each of which was had an idea in it about a language for engineering, where language meant something much more general than something like the word scheme or C or anything. Okay, so the languages were basically kind of programming. Another one was sort of electrical circuits. Another one was signals and systems type stuff. And another one was computer architecture like stuff, okay? Which are languages in the sense that one of them is about how to do things, okay? Another is about how combinations of pieces make bigger pieces that are also pieces. That's what electrical circuits are really the best language in that sense, okay? And then the signals and systems thing was about composition of functions and feedback, okay? And the computer architecture thing is a bigger picture of all, okay? About things like balancing loads and stuff like that, okay? That was a very nice, and that ran from 1980 to about 2000, okay? However, and 6001 was which I invented, and then I got Hal on, and so that went from 1980 to 1997. We both became rather tired of it, having done it for that long, although we did other things also. So we sort of quit, to be perfectly honest, in 1997. The reason why we thought it was sort of out of date at the time, and we did, is that engineering had changed drastically over the period of, say, the 1990s. In a way that was sort of discontinuous. And I'll explain what that was like. At the beginning of the 1990s, there were still resistors, transistors, capacitors, inductors, right? And you could put them together and make bigger things out of smaller things, and you knew what every one of the things did. That is, there was a very clear description. If you got a chip, you got it out of the TTL data book, it had at most 20 pins, and there was a one-page description that was perfect. Okay? By the end of the 1990s, all of a sudden there were 1,000-pin chips with manuals this fat, and the person who wrote the manual didn't know what was inside the chip. Okay? And the person who designed the chip didn't know what the manual was going to be. So they were inconsistent, and furthermore, there was a lot of top secret stuff in it that you couldn't find out anyway. Okay? So that's true also of programming. At the beginning of the 1990s, continuing from the past, things were made out of little parts like addition, subtraction, multiplication, division, cons, calculator, stuff like that. At the end, there were these enormous libraries of things like graphics libraries and this, that, and the other, with thousands of functions written into giant manuals. Okay? And so what I discovered around the middle of the 1990s was my students were spending most of their time reading man pages. It was a very different thing from the kind of programming that we were teaching. Okay? So what I suppose the answer was that it seemed to me that the change in the engineering type that that was needed in the future was no longer so much pressure on understanding how a bigger thing is made out of smaller things by combining the parts and understanding that from the way the parts work and the ways they're put together, how you get something bigger to work. That sort of analysis and synthesis view, okay, to one which is more like science. You grab this piece of library and you poke at it. You write programs that poke at it, see what it does, and you say, can I tweak it to do the thing I want? Which is what we do now a lot. Mm-hmm. Okay, and that was true of the chips as well. So it seemed to me that sort of we had the kind of engineering we were doing, it was although still important intellectually, it was no longer relevant to the kind of things people needed. Okay? So I suppose Hal and I basically walked into the department head's office on sometime in the end of 1997 and said, we quit on this, okay? Figure out what to do. For 10 years after that, they couldn't figure out what to do. The department head himself taught the class. This was Grimson, Eric Grimson, very smart guy. But his heart wasn't in it because that wasn't his thing. You know, and the most important thing you have to do when you get people teaching a class is you get the people who teach the class to be the people who want to teach that class. Okay, that's their thing. Committees were formed, and committees do their things, and so on. And it was determined that the right thing was to worry about essentially I/O-driven type stuff, which is probably true, where you have things where there's sensors and there's action and there's something like little robots and there's uncertainty due to the fact that the motors aren't exactly right, they're not perfect, and so on, and they're not well specified, and that's right. So there was a hunting around for some people who might want to put something like that together. People did, and that was mildly successful. The difficulty with it is that it didn't produce a very coherent structure. Like the 6001 was a very coherent structure. In fact, the four course in the introduction to electrical engineering and computer science that we had previously was more coherent. And we're still hunting for the right thing now. Okay, but we don't know what the right thing is. It's not like we have engineering made a big change and we have to find out a way to do it. Okay? The reason why Python was chosen at the time was it was for exactly the reason Python made it in general. It was enormous libraries for everything. And therefore you didn't have to, it was a late binding decision. Okay? Okay? That they basically, which is the right thing. That because of the fact that for reasons no one understands, all of a sudden Python acquired this enormous library structure which allowed people to say, I'll make a thing that does this, that, or the other thing, and they found all the stuff they wanted. Okay, in particular things that could move a robot around. How's that? Yes?
So you spoke a lot, mentioned danger. You had dangerous techniques, dangerous ideas, and pursued them. What is the connection between robustness and danger? How can you push that biological metaphor further?
Well, I think I actually am working on that very hard. The essential idea there. Did you want to answer the question? Oh, he's asking what is the connection between the robustness and danger, okay? That is illustrated by the biological metaphor, okay? And of course, the answer there, as far as I can see, is nothing is perfect, okay? However, to make something that always does as reasonable a thing as it can under the circumstances, which is exactly, you know, I did put on the abstract for this talk, Postel's law, right? Which is that you should always be generous in what you accept and very particular about what you put out, okay? Because that means that you could build a system which has lots of flexibility in the sense that every part is trying its best not to be the thing that kills the system. It's trying its best to do what's reasonable at the time. The difficulty with that is that it encourages people to stick on, you know, to play on the corners, right? It encourages out of band behavior by people who don't have to. Now we got away with this in digital electronics by inventing what we call the it's the fact where the voltages are in the right place. There's a name for this. I just lost it.
Threshold?
No. No, sorry. I'm talking about the what's called static discipline. That's the word. The static discipline. Okay, where the outputs of a digital device are constrained to be much narrower in what they are allowed to be than the inputs that they must accept. Okay, and that's for all devices in a family, and that leads to extreme noise immunity. Okay, that's a beautiful example of Postel's law. Okay, and indeed the reason why we works in the digital world is because the manufacturers choose not to play games on the corners, because what they end up doing is they lose their noise immunity, which is a big selling point. Okay. The problem is computation. It's hard to make it a selling point that you, by tweaking this thing, it'll still work. You know, by trying it on something that you didn't expect, it would still work. That's a very hard thing to sell, but I think it's probably the right thing. Okay. Is that a good answer to your question?
Well,
why don't you stand up and talk louder so he can hear you in the back?
so I'm wondering much more about how professional programmers, developers, incorporate this notion of danger in their work, and how does robustness, this notion of robustness, generic-ness, and flexibility arise from taking those risks?
Gee, I don't know is the right answer. I could say that most things that are built don't have to be perfect. Okay? I don't think it would matter very much if 1% of all the queries that were accepted by Google didn't work. Right? It just doesn't matter. Okay? What matters is that it always produces a reasonable result. And I think the people like that know that. They do the right thing. I think that the place where we have to worry is a couple of places where there's legal requirements, like banking. Conservation of money in a bank is important. The conservation law, right? The conservation law is imposed by law.
I only ask this because I run a fintech startup with computational law and finance.
Yes.
We build expert systems which try to reduce risks.
Of course.
But
yes, of course. And so that's an example of a case where you have to be exactly right. Okay? There are cases where people think they have to be right, like in autopilots, which I disagree with. Okay? And there are places where people are pressured to be exactly right in things like medical devices, which is probably hard to argue because the patient was going to die anyway. But you know, what the heck? Okay? You know, it's very hard to deal with that too. So I think that the question of how much risk you should be allowed to take partly is determined by how many lawyers are breathing it out of your neck. Okay? Yes. Yes, sir? You want to talk loud so other people can hear you?
I was wondering how this relates, your talk relates to the propagator model.
That's a plumbing model, actually. He asked about the propagator model, which is a thing that was worked on by me for many, many years, starting with Richard Stallman in 1975, actually, when I hired him to work for me when he was an undergraduate at Harvard. We did electrical circuit stuff, and we made little programs that were where the way the program worked is a little box would look at some of the cells around it and say what values are in them and make deductions, okay, based on them, and carry the dependencies around. That was a good thing, and the most recent advances in this were done by Alexei Radul in his doctoral thesis in 2009. But we also had, Guy Steele's PhD thesis was about that too, about constraint propagation and so on. So I've been worried about this for a long time. It turns out that is not connected to what I'm saying about today, except for the fact that all good programs, I think, should be very generic in the way they're built. Generic operators are crucial, and user programmable generic operators are crucial. Now, what the propagator thing is an alternate way of plumbing systems. If we look at things like Lisp, or almost all languages we know, okay, they are expression languages, meaning that the output of anything is one thing. Yeah, we can fool around and have multiple value returns, but basically it's an expression machine. Okay, it's a funnel where stuff comes up from with lots of inputs and produces outputs. Okay, the propagator idea is one where you are not dealing with fundamentally trees, but you're thinking about networks of machines that talk to each other. Okay, and that gives you a little bit more flexibility. And again, one of my goals is to figure out ways to make various tools that can flexibly operate with each other. I can imagine that each tool that you use makes a little propagator box for the program it's running, but the way they talk to each other in a way that allows them to cooperate involves a different kind of plumbing. Okay? More of an electrical engineer's view of the world. I want 50 ohm cable with BNC connectors. Okay? Got it. Yes, sir.
Has anyone started to do a
for when you can, when we have to be exact versus when the system can have some sort of tolerance or be robust in these kind of problems?
I don't know. I certainly haven't. Okay. However, there's a good piece of work for you to do. Okay. I think it would be nice to figure that out. I have no idea. Yes, sir.
On the previous question, would you please expand a little bit more about the propagator?
Oh.
And even give an example.
Yes. Okay. Well, what I don't have here is a chalkboard, but that's okay.
You actually have one.
Oh, he wants to know more about propagators. Okay, that's. Oh, there is. Oh, well. Okay. Okay. Yeah, I love writing on. I don't like whiteboards, but chalkboards are really better, and they're much better. And the reason is because chalkboards don't smell. No, they're dusty, but they don't smell. Remember, chalk is basically Tums. Yeah, it's pretty harmless. Okay, so the propagator idea, which is that the world is made out of little autonomous machines. You can think of these as these little machines, okay? And huh?
By machine you mean a computer?
Well, maybe. Okay. Maybe an electrical circuit. I don't really care. Okay. A computer just is an electrical circuit that happens to be universal in its ability to be programmed. Yes. It could be something like an x86 for all I care with a gigabyte of RAM. Okay. That's yeah. I mean, and then these things, you know, they talk through things called cells. Yeah. So that say this guy. You know, this guy talks to this guy. Okay, there's these cells that they talk through. You know, and the goal is so these little machines are green and the cells are black. Okay, the cells are not repositories of a single value. They are repositories of information about something. Okay, for example, they could be information about the height of this beer bottle. Okay. Now we maybe have many ways of measuring the height of the beer bottle. We may, for example, look at the light coming down from it from that lamp, and look at the shadow, measure the length of the shadow, and have compare it with a known measurement that's in the same place, and see what the shadow is there, and use similar triangles. We might measure the height of this thing by putting a ruler next to it and seeing. We might measure it by I don't know. I can't think of lots of things for measuring the height of a beer bottle.
Google it.
Good, we can Google it. Right. Right. Oh yes, that's right. We can do this. I can't do it, but yes. Okay. You can measure the frequencies. There's a whole bunch of things that you could do with a beer bottle. Now the thing is that these might be, in some sense, degenerate ways of solving a problem. This might be a thing that's interested in the height of the beer bottle. This might be one way of computing it from certain information. This may be another way of computing it from this information, okay? This might be a contributor that's getting from somewhere else, okay? And so what's happening, what each of these little machines is doing is examining the things it knows about, the cells that it participates in, okay, determines whether any of them has enough information to allow it to make a deduction where it can change a value in one of the other cells, adding new information, not the same as changing it. It adds new information, it contributes that information, and the cells have a means of merging the information. So, for example, if the kind of information about the height of the beer bottle was something like a range, okay, say an interval. A numerical interval of centimeters. Okay, then the merge would be something that intersects them. Okay, producing a better answer. Okay, it also carries the way in which these propagators mostly work is they also carry the provenance of the information that they're combining. So you could say the reason I believe that this is this high is because these two measurements give me information that are overlapped in this way. Okay, and you can actually get the thing to type out that kind of information for you. So that's the sort of, I consider that a kind of plumbing for mechanisms. The mechanisms themselves can be arbitrarily complex or simple machines. See, I'm not worried about what's in there. This one can be written in Fortran for all I care, and this can be written in Haskell, and it all should work. Okay? Yes.
Truth maintenance come in?
Yes, truth maintenance is one of the what? Yes, he's asking about truth maintenance, which is again the thing that came up starting with Stallman and me, and John Doyle was my student, and he wrote a master's thesis about this. Gosh, 1976 or something, and then David McAllister wrote another master's thesis about this later, and then Forbes and DeClear wrote a book about this stuff called, and they were my students also. What was that? That was called called Building Problem Solvers. Okay, that book. Anyway, but the whole idea there is that when you combine the information, you also have to be able to combine the provenances in the right way, and that means you have to carry the dependencies correctly. And truth maintenance is a way of making sure that you've got this right. Okay, there's whole books about it these days, and a lot of SAT solvers have figured this out too. But we did it first, I suppose. We didn't realize we were building SAT solvers at the time. Yes.
So Doyle's paper proves that it's an NP-complete problem.
Of course.
Gotten better than that, or?
Oh well, no, but everything's an NP-complete problem. I don't care about that. Okay. The real question is whether or not it's tractable for real problems. And so, let's see if that's a beautiful example of that. Right, people do use SAT solvers now.
Yeah.
3SAT's terrible, right?
Yeah.
Yet they use them to great effect.
Yeah, untold
right?
problems. So
right. The real answer is that if I'm going to sort with a bubble sort, it's a terrible way to do it unless I'm only sorting 12 elements.
Right.
Okay, and that's the right way. Okay. Anybody else want to talk, or should we adjourn? Yes, sir.
So
Pick up, stand up, and so people hear you.
I can project.
Okay.
So the nature of computation has evolved a great deal since the 80s. Historically, for example, in the 80s, let's say the state-of-the-art in parallel computing was something like the connection machine. Interestingly developed by people like Hillis,
yeah.
who later commented, that Feynman once commented, you know, computer science is going to be a lot better than physics. It has locality of reference, it has a certain built-in durability, it has a sort of adaptive and graceful degradation the way physical principles do. Now, today, the scale of computation is very different. It's routine for a student to have access to 100 and corporations to have access to hundreds of thousands of nodes of computation.
Absolutely.
That have a far more statistical coalescing quality. There's less determinism, there's less guarantees about resiliency and actual system performance, as well as aggregate performance. How do these paradigms, in your opinion, map onto these modern scaled problems, which are inordinately larger than we saw?
Actually, the reason why I think the propagator thing actually does scale directly, because there's no reason why any of these machines have to be in the same place. There's no reason why these little lines that you say there can't be network connections. Okay, this thing scales from the level of chip scale to arbitrarily large. Okay, but I don't think that. Again, I'm being very careful. I don't think I have an answer to all the world's problems. Okay, and I want to be very careful to say that don't let any magic bullet. Don't shoot yourself in the foot with a magic bullet. Okay, I have some magic bullets I'm playing with now, specifically propagators, but I think that they're dangerous. They're easily, one can easily get addicted to them as easily as one can get addicted to Bayesian networks. Okay? Yes. Say the right thing to do is be very careful and see what problem you right tool for the right problem. Yes, sir, in the back.
Are you coming to the bar after the talk?
I haven't thought about it. Okay. I generally don't drink particularly. But I don't. Huh?
There's definitely food. Yeah, you don't have to drink it.
No, I am slightly hungry.
Yeah.
So sure.
Yeah. Okay. Awesome.
Okay.
Announcement about where it is.
Okay. Does anybody else have anything? All right, I propose we adjourn. Any second?
Let's have one more.
Okay.
So I'd like Gerald Sussman for speaking tonight. It's a pleasure to have him. Folks, please, there's a lot of us here, so please make sure you pick up your trash on the way out. Let's leave nothing but footprints. I don't even need footprints. And for those of you who want to join us at the bar, we're going to be heading over to McKenna's Pub. That's on 14th Street.
Shut this down. Good.
Yes.
My name is Brendan Riley. I work with Dave Farber, and I also work with John Foster.
Oh, good. Yes, he was a great man.
Did you work with Charles Rich?
Charles Rich was my student.
So he